Hi everyone, my name is Arno Saxena, and today I'm going to talk to you about Lab 5. So for the introduction, the goal of this lab is to use the concept of Faraday's law from a falling bar magnet that is falling through an aluminum wrap tube in order to derive the force on the external magnetic field and also the induced current. The physics principles that we're using for this lab are Faraday's law, Lenz's law, magnetic force, magnetic fields, magnetic flux, as well as Newton's second and third laws, as elaborated on in the slides following. The materials that we used were a bar magnet, a smartphone with the magnetometer app, a ruler or meter stick, and a roll of aluminum foil around the cardboard tube. Setting up the experiment. So for the experiment, we used the magnetometer on our smartphone to find the orientation of the bar magnet's north pole, as shown in the visual to the left. This will then point downward as it's let go and falls through the aluminum tube. Dimensions of the tube are a height of 30 centimeters, a diameter of 4.3 centimeters, which includes the foil thickness, and the actual tube is 1.4 centimeters. So here you can see the specific time trials that I obtained, and all 5 of them are averaged out to obtain a time of around 3.436 seconds. So for our computational model, we wanted to represent the bar magnet flowing through an aluminum tube. So we first start with the constants that were given, and then we put in our specific values for length, width, and also the inner radius. And then using the mass and also the magnitude of magnetic dipole moment that we were given from Lab 3, we can then use this to list out an equation to find the actual magnetic field of a bar magnet. And then also using the lecture 43 details, we can also map out the rate of change in flux for this specific equation. So after this, we then create a simulation loop which calculates the gravitational force on the magnet, the magnetic force, and also the current. From this, we can then get the B field, and this will then update the actual net force and as well as the magnet's velocity, which is plotted on the graph. Here you can see in the picture that the computational model was around 4.89 seconds, which is slightly more than the experimental time of 3.43 seconds, or 3.436 seconds. So for the conclusion, what happens to the dynamics of the system when you flip the magnet around? So changing the orientation of the magnet will change the direction of the currents, since we take into account the south side of the pole being fallen through the aluminum foil, as opposed to the northern pole. And how does the total time and tube of the real-world system compare to the computational system? So, and also how will this be more accurate? So the computational model time is slightly more than my real-world time. In order to take into account the actual difference, we can list out the approximate height at which the magnet may have been dropped to include a set of ranges, as this might not have been held constant in the actual real-world experimentational model. So the shape of the velocity versus time tells us that the force of the magnet is held constant, since velocity will increase linearly, and as acceleration is a change in velocity, and we can see that since this specific value is held constant, acceleration is also thus held constant, which when multiplying by the mass will give us the force of the magnet that is constant as well. So if the resistivity of the conductor was reduced out to almost zero, then it would fall through, or then the magnet would fall through completely as without the fold, since there would be no actual change due to the conductivity of the actual aluminum around the cardboard tube. And if there were holes or slots cut into the tube, the ring currents, then the ring currents would actually change because the magnet wouldn't obtain a constant increasing velocity, as the resistivity is now changing in specific parts of the tube. And since the tube isn't constant, this thus affects the actual ring currents in our model. And that's all.